Right, so welcome to this lecture on random processes. Last time we started the module of two very important random processes, which were Poisson and Gaussian. Yes, one is both of them are continuous time, but where is the difference? One is discrete state, being Poisson, and the other is continuous state. Yes, so last time we basically did not discuss the processes themselves. We mainly discussed the underlying or the background information about them. Yeah, the Poisson distribution, exponential distribution, the Gaussian sorry, distribution. So today we will build on that knowledge to continue our study or into Poisson and Gaussian processes. Yeah. So I did mention in general what was it that the Poisson process was, let's say, representing. तो क्या होता है mainly क्या idea है Poisson process का? What is it? It's a
continuously increasing it.
right. So what does it represent? It is like, is it a counting process? क्या है?
It's a
क्या
counting
बोलेंगे?
process.
Okay. So it's a counting process where there are arrivals, right? What's the condition which makes that counting process a Poisson process? What was the condition on arrivals or arrival times? So they had to be IID and so the Poisson process, yeah. And we also saw the law of rare events that describe the Poisson distribution, right? So now we are coming to the Poisson process. Basically, again, it is what? It is a process that keeps count, let's say, these are times, so that's fine. Okay. It's a process that keeps count of the events that are occurring. Yeah, and the events are basically, we are just counting them, so it's not it does not count down, no decrementing. Yeah, so let's say it starts at 0, one event occurs here, another event occurs here, another event occurs here, another one occurs here. Yeah, so what does it do? Up to here it's at 0 because the count remains 0, no event had occurred. Then one event occurs and the count is now locked at 2. Yeah, when the next event occurs, then the count goes to 3. ये तस्वीर में आप टिक टिक कर दें. Yeah, so that's the idea. So this alone right, and then here and so on. This thing alone does not make NT a Poisson process. It makes it a counting process, yes, but not Poisson. What is that requirement? These intervals, right, have to be IID 1 second exponentially distributed. So basically that is what we're going to write here. Let's call one interval between two events as xk, tk minus 1. Right, so x4 will be this gap. Yeah, x3 is this gap, then this gap. So we're saying the intervals between two events are IID. That's one thing. And what is their distribution? fxk x is, what's the distribution of J and B? Gaps की exponential. Yeah, so I'm going to use lambda prime because we need lambda for the Poisson process. Otherwise it's remember we had a lambda thing. Okay, so E minus lambda prime x, x greater or equal to 0 and 0 for x less than 0, because the intervals cannot be negative. Yeah, the way we have defined, so you cannot have them negative. So what I have been telling you from the start, it is now written mathematically here, and we have already discussed the Poisson distribution. Yeah, sorry, the exponential distribution and the Poisson that will come. So these gaps, if they are IID and exponentially distributed, then as a necessity, NT will be a Poisson process. Okay, and what will be the distribution of that process? Well, firstly, what does NT represent? It represents number of events in 0 to t. Okay, so NT4 means the number of events from 0 to t4, how many have occurred. Yeah, and if that happens, then can be proven. I am not doing that here, but can be shown that in that case NT is Poisson distributed with arrival rate lambda. Okay, where how is this lambda related to this lambda? Actually, it's the reciprocal of this 1 over lambda prime. Okay, again, I didn't prove it. You can find the proof in your books. Kobayashi and I think also Lindgren has it, but you can check. From here you can work on the distribution of the total count of events, and it will come out to be Poisson, and the parameter of Poisson, the lambda, will be related to, because you will start derivation from here, so this thing will show up in 1 over lambda prime form, which we now call lambda for the Poisson distribution. So what was the Poisson distribution then? Probability NT equals K in, let's say this is the interval, we can generalize it also, okay, in interval H. Maybe you don't want interval to be always 0 to, right? You want some interval of length H. Yeah, in that case the Poisson distribution, we looked at, we had T here. Yeah, so now we just want to define some interval, so K E minus lambda H over K factorial. This is the distribution जो आपने देखी थी. But the thing is, what we are saying now is that NT equals K in interval H can be calculated from Poisson distribution, and we will call NT as a Poisson process, right? So this, the evolution, this thing going like this thing is the Poisson process, okay, whose value in interval H can be calculated using the Poisson distribution. Yeah, and its the relation to exponential we have discussed. Now there is another way of defining Poisson distribution. Usually it is also covered in textbooks, so I want to cover it, but it takes a while. So there is an alternative way of reaching the same conclusion, okay, but I find this simpler, but let's do that for the sake of completion, because that will come in handy for Wiener process also. You know, it's very common in mathematics to have different kind of proofs for the same thing, or to different starting points leading to the same conclusion, right? So this is what's going to happen now. We're going to start slightly differently and reach this same conclusion. We say that a stochastic process, here I've written xt, but we could also write nt. We're actually talking about this guy. So just to be consistent with what I have in my notes. This is still a process, a counting process, xt. Okay, suppose there is a stochastic process xt with t in some continuous t. Okay, there is some stochastic process. If this stochastic process satisfies three conditions, okay, then it necessarily becomes a Poisson process. Okay, first condition is that it has independent increments. Another reason I want to cover this approach also, it has at least three terms, two or three terms that are often showing up, not very often, but at least showing up in study of stochastic processes. Okay, so if you know those terms, they will show up in other places, then you'll be comfortable with them. One is independent increments. Okay, so there is a stochastic process. Yes, it's continuous time. Other than that, we have not said anything yet. Now we are putting three conditions on. Firstly, independent increments. What does that mean? That means that, let's say, xt2 minus xt1
doesn't depend x3 minus x2
is independent of xt3 minus xt2 and so on xtn. All of these are independent of each other for any selection of t1, t2, tn, but that are non-overlapping. Okay, so what we are saying is that non-overlapping intervals, the number of events in non-overlapping intervals are independent. Okay, so number of events in, of course, if you overlap them, then there will be some dependence, because this part of the interval is same. We're talking about what would look like a non-overlapping intervals, for example these ones, right? So the number of events occur in any set of, if you want to draw like this, fine, yes, these are non-overlapping intervals. You could even make it one bigger, some smaller, fine. As long as this 3 or 4 are non-overlapping, the number of events occurring in them will be independent of each other. Okay, that is like saying that the arrivals are not affected by what's been happening before, right? So it's kind of a pure randomness in counting. Yeah, so number of events in non-overlapping intervals are independent. That means if 4 events have happened here, there is nothing saying that there will be no information or no, let's say, dependence on how many will happen here. Okay, as long as they are non-overlapping. Okay, so they have independent increments. Second is they have stationary increments. Stationarity तो याद है? Stationary increments. We will say that here, that means that the distribution xt plus h minus xt, that is this representing number of events in interval h, right? So the distribution how is this distributed depends only on h, or we will need some x, but otherwise it only depends on h, the length of the interval. Otherwise the distribution does not change. Whatever the distribution is of the number of the increments over any given interval, those distribution remain the same. What does that mean? Basically we are saying that if you want to look at xt1 plus h minus x, let's say t1, some, let's say T1 is here and H is here. So this is the number of events that occurred in interval H, but where did this interval start? At T1. Let's say you find some distribution for this. Okay, let's call that F1. Yeah. So you find some distribution for this. What this is saying is the distribution you find for any other T2, T3, T4, Tk, yes, Tkh minus xtk will be exactly the same. There is stationarity, yeah, in this sense, that the distribution does not depend on the actual value of the where the interval starts. So the number of distribution of the number of increments in this interval or this interval or this interval will be exactly same as long as the size of the interval is same. Yeah, so it only depends on the size. That was a kind of thing which we saw in stationarity also. The covariance, remember, had to depend only on the time difference, not the actual time. So this is what's happening here. What are we saying? What does it depend on? Only h. If you look at it, isn't that the time difference here? T1 plus h minus t is h. Tk plus h minus tk is h. That's why the distribution remained fixed. So we're not saying a process, any process has to follow this. We're saying if there is a process that satisfies this, and now the third condition, if it satisfies all three, it is what we call a Poisson process. Okay, so what's the third condition?
Can you elaborate the difference between first and second conditions? थोड़ा सा इनके दरमियान थोड़ा सा difference बता दें. मतलब यहाँ सेकंड में हम ये कहना चाह रहे हैं कि हमारे पास जिन जिन में डिफरेंसेस हमारे पास सेम होगा उसमें डिस्ट्रीब्यूशन सेम होगी.
हाँ जी, डिस्ट्रीब्यूशन इस गैप पे सिर्फ डिपेंड करेगी, राइट? यहाँ पे डिस्ट्रीब्यूशन की बात ही नहीं है.
डिस्ट्रीब्यूशन डिपेंड सेम ही होगी, मतलब डिपेंड करने का मतलब ये जिन जिन में गैप्स हमारे पास सेम होंगे.
हाँ, उनकी एग्जैक्टली सेम होगी. So whatever distribution this guy has, the same, if you replace t by t prime in both places, that will have the same distribution.
और ऑलमोस्ट वो सेम ही जो हमारे पास डिस्ट्रीब्यूटेड होंगे इंटरवल्स जो हैं उनके दरमियान डिफरेंस हमेशा सेम होगा, डिफरेंट बढ़ भी सकता है कम भी हो सकता है हमारे पास.
नहीं, इंटरवल तो आप कोई भी ले सकते हो, right? But let's say you lock the interval, you say h is 10 seconds, right? Then it doesn't matter if you're looking at these 10 seconds or these 10 seconds or these 10 seconds. The distribution of the number of events that occurred in those 10 seconds in each case will be the same. The distribution will be the same. The actual events may vary. Distribution का concept समझ रहे हैं ना? जैसे coin toss करने की distribution क्या होती है? Uniform होती है. Doesn't mean कि head और tail हर दफा आते हैं या क्या है, right? Actually, the actual number may vary in them. The number of events may vary, but the distribution they follow will be exactly the same. Right? Here it's not talking about the distribution at all. तो कह रहा है कि वो independent होनी चाहिए. अब हमने independence we have discussed in great detail, right? उनकी क्या है, there are many tests for it. Their distributions are separable. What I like to see here when we talk about independence from a practical point of view, usually we are saying that the knowledge of the previous intervals happenings does not help us statistically say anything about the next interval. ये होता है, या उसका distribution से ताल्लुक नहीं, ठीक? पर और इस पे सोचें आप तो आ जाएगा. Right. So what's the third condition? That is, of course, remember so far we haven't put any condition on it to be a counting process or anything. ये different approach है ना. यहाँ तो we started by saying NT was a counting process, and then we said okay, what are the two conditions that would make it Poisson? यहाँ हमने कहा any stochastic process just continuous in time, right? So that's why we need this third condition now. The third condition is going to say that if the process is also, ये term भी interesting, simply increasing process है, So it has the simply increasing property. Again, I could have skipped this whole thing because आपने Poisson काफी हमने discuss किया, but I wanted these terms. Okay, because there will be other processes, yeah, other situations where you need to define these properties or use some of them. Okay, जैसे हम stationarity already use कर रहे हैं, independence already use कर रहे हैं, right? So moments use करते हैं बार बार. So what you learn here, these will show up in some other processes also. So conclusion is going to be Poisson process, which you already know from another definition. So it's not really too much useful, but the concepts here or the terms, it's good to have them. भूलता नहीं है बंदा, अभी होता है आपको लगेगा कि आप once you've done this you'll forget. 10 years from now maybe you're working on something and it says okay there are stationary increments in this process, फौरन क्लिक करेगा कि कुछ था सही, और जब आप रेफरेंस देखेंगे बड़ी तेज़ी से वो फ्रेश हो जाएगा, right? Compared to someone who never heard it 10 years ago, उस बंदे को टाइम लगेगा ज़्यादा समझने में उन्हें, right? So simply increasing property, that has two parts. Firstly, it is, we are saying that if there is a stochastic process continuous in time such that it has independent increments, it has stationary increment, and it has the simply increasing property, which means that it is non-decreasing with integer jumps. Okay, ये जरूरी है अब ताकि now this will now become a counting process in a way. Okay, ये तो हो गया increasing property का.
इंटीजर जंप मस्ट होगा इस कंडीशन में.
Integer jumps, why?
काउंटिंग के लिए.
Yeah, counting, that will make it a counting process. Remember, if we don't have this integer jump thing, it is continuous time, but what makes it discrete state?
Discrete states.
वो अभी नहीं आया था ना, तो दूसरी डेफिनेशन है उसमें ये हम सारी चीजें ज्यूम करके शुरू करते हैं कि काउंटिंग प्रोसेस है उसमें यही होना था, right? Here we have to build everything from scratch, right? So that is the part saying non-decreasing with integer jumps. But what's the simply thing here? इसका क्या मतलब? आपने नोट किया कि मैं whenever I draw the Poisson process, I always allow just one event. 6 लोग इकट्ठे नहीं आ जाते, right? Okay, so that is the simple. Compound increasing is when you allow multiple events to happen at exactly the same time. Yeah, whereas Poisson, the way it's defined or set, it's a simply increasing process, meaning it only, here even this doesn't say that integer से मुराद ये तो नहीं है कि 1 से 2 ही जाना है, 1 से 12 भी जा सकते हैं, integer ही में रहे ना, we're still in integer, right? But then what protects it from those bigger jumps is simply this simply thing basically. Yeah, simple. Yes, simple means not compound, not compound jumps. Basically simple is a compound के opposite में use हो रहा है, right? So उसको लिखते बड़ा मजे का ये, क्योंकि mathematics में we don't like to write things in a simple way. So the probability of more than one event occurring in an infinitesimally small interval approaches 0. Okay. So basically we are saying probability xt plus h minus xt is greater than 1 over h, okay, it approaches 0 as h approaches 0. Okay.
ये h क्यों सारे हमने किया? h के बगैर भी तो हम इसको कह सकते हैं, मतलब कि विदाउट h अगर मैं h रिमूव करूं देन भी तो डिफरेंस हम ये कह रहे हैं कि
अच्छा इसमें ये है कि ये मैंने शायद ये भी लिखना है approaches 0 और ये almost surely sense में वो आ जाता है, right? So without h, let's see, probability xt plus h minus xt greater than 1 approaches 0. I think just to avoid degeneration here, if you do it without h, you are making h extremely small. So um, I think it has to do with scaling, because by making this something small, you decrease the chances of the event occurring anyway, right? So you have to keep it at level with the other intervals. Bigger interval में chances high होंगे किसी चीज़ के होने के. As soon as you make the intervals very small, not just this, anything happening becomes very unlikely. So then you normalize with the size of the interval. समझ आ रही? डेरिवेटिव में भी यही आइडिया है ना, वो क्या आता है, ये डेल्टा टी इधर वो हटा के देखे आप, वो काम नहीं बनेगा. Right? So, but does anyone know what this is? As h approaches 0, why not this arrow? एक ये भी arrow होता है ना?
Yes sir.
इसमें क्या फर्क है? गैस कर लें, तुक्का लगा लें जल्दी से. Just a mathematical notation to also give another information other than h approaching 0.
It's approaching from right to left.
Yes, ये negative तो हो नहीं सकता. If you know mathematics, when you say h approaches 0, you're not talking about is from 0 minus or 0 plus. This is definitely coming from 0 plus because it's by definition an interval. Yeah, so it just carries additional information to make sure. Yeah, okay, good. So this is simply increasing probability of, as the interval gets smaller and you normalize it, the probability of two events, more than one events occurring becomes almost, that means two events may occur sometime, right? But almost surely नहीं होगा ऐसा, right? But what's the conclusion? Well, the conclusion is that if all three are satisfied, then this guy that we started with, saying some stochastic process in continuous in time, if we put all these three conditions here, then this process becomes Poisson process. और इसकी distribution exactly वही होगी जो हम already निकाल चुके हैं through the what we found through the other method. Okay. Now, in addition, I will not prove it here, but we can show that some properties of the Poisson process. Yeah, I'll have to take this away, but it's there in the books itself. Actually, when we teach some Poisson process in earlier courses, also we actually teach this definition.
This notation is in Gaussian book. Gaussian book की सर कुछ आपकी notation ली है h limit
ये वाली मुझे अब याद नहीं, one of them, check, maybe it's Lindgren, I think, Kobayashi, I'm not sure if it's him. Right, so some properties of the Poisson process. Firstly, let's see, if you now we have, let's say, established that xc is a Poisson process. Okay, we, let's say, it has satisfied all the conditions, a Poisson process. Then we may be interested in finding, okay, what is the mean of the Poisson process. So I'm not deriving it here, but it turns out to be lambda t. Okay, one thing. What is the covariance? याद है R S T. What was that? Covariance of x s x t. Yeah. What is that? It turns out to be, it has to be derived automatically. Lambda min s comma t. From here, can you tell me, is the Poisson process stationary or not?
stationary or not? No sir, it depends on
जी, एक तो नो आ गया और सिंपल आंसर होगा. स्टेशनरी क्या क्या चेक करते थे? What were we checking?
constant
Time. क्या कांस्टेंट होना चाहिए इसमें?
मीन होना चाहिए
mean should be constant.
Yes, नहीं होगा sir.
नहीं है नहीं, right? So basically it fails both tests.
Yes,
Mean should be constant and the covariance should depend only on the time difference. Yeah. Now look at it here. Already it fails. So mean is changing with time. If you are looking at the process, ये है ना process. xt से अभी क्या मुराद है? The value you see, let's say this is t. Yeah. So what we're saying is xt is the value you see at time t. The value you see at time t is arrival rate times t. So the value you will see here will be the mean value. So the mean of the process up to here and the mean of the process at this point, it will be different. Yeah, and that makes sense क्योंकि increasing process है ना, तो उसका mean तो ऊपर जा रहा है, नहीं? टाइम के साथ साथ ऊपर ही जाना है, और कहाँ जाएगा? Right? काउंट करते जा रहे हैं ना. So the mean here is low, but the mean over here should be higher, क्योंकि वो arrivals होती जानी है ना, कुछ तो होनी है, randomly होनी है, पर होनी तो है ना, तो वो that makes sense. What about this? Does this say that the covariance depends only on the time difference? नहीं ना? Look, some students confuse this. They think it doesn't depend on the actual S and T. It depends on the minimum. But the minimum, let's say S is 10 and T is, let's say 15, right? Then it will pick what? 10. Yeah. So the difference here is 5. Yes. What if S was 20 and T was 25? Difference is still 5. For a stationary process, whatever formula comes out should depend only on the difference. That is 5. If these are both 5, then the covariance should come out exactly the same. In this case, first one will give you covariance lambda times 10. The second one will give you covariance lambda times 20. So it fails the other test also. Yeah. So it's a non-stationary process. That is there. So we talked about simply increasing, right? So just a last note I have written here, parting note. So basically, Poisson process does not apply to situations where you actually expect events to really occur in clusters, in groups. Okay, then you have to either generalize the Poisson process or work with some other kind of counting process. Okay, so I leave that as a homework for you to find a couple of those processes or distributions, or what do we use if the events are occurring in, allowed to occur in clusters, or compound increments are allowed. Just you don't have to solve anything there, just try to find a few just as a curiosity. Okay, so yeah, that can be here. Right, so that covers the Poisson process. Yeah, and as I said, there are of course some proofs that you have to read up, but my method usually is to cover the main concepts. Yes, and then you can of course go through the steps of finding how do you get from the Poisson distribution to this thing, for example. Okay, so those you can just see in a book, see the proofs there. Right, so the second process we have been talking about is what? Gaussian, the normal process. Last time we talked about the Gaussian distribution. It was a consequence, or its importance was really embodied in the central limit theorem. Poisson कहाँ से आया था? Law of rare events. Interestingly, सेंट्रल लिमिट थ्योरम से रिलेटेड एक है लॉ ऑफ लार्ज नंबर्स. So it's very easy to remember. Poisson law of rare events, Gaussian law of large numbers, and its cousin the central limit theorem. Okay, so बड़ा interesting और easy चीज़ है. Right. What was the first difference? Gaussian was continuous time, continuous state. And it's not a counting thing. Yes, that makes it a continuous state process. So, what's your guess? What would be a Gaussian process? We know a Gaussian distribution, right? We did that last time. So, if a random variable is Gaussian distributed, we are saying that
The first property will be same.
Mhm.
Independent increment.
Yeah, that we will do when we develop the Wiener process, which is a special case of the Gaussian process. Gaussian is more general than these properties. Exactly this kind of properties, if you assign them to some process, it turns out to be a special kind of Gaussian, the Wiener. We will see that. Yeah? Here, the Gaussian is more general. Okay. So, firstly, the distribution. What's the Gaussian distribution? If a random variable x is Gaussian distributed, how does its distribution look? याद हुई है कि नहीं Gaussian अभी तक?
Minus mu
Mm-hmm.
x minus mu over sigma square. E power minus x minus mu over.
So if x is Gaussian distributed, we are basically saying that the probability x takes the value small x depends only on two parameters, mu and sigma square, in this precise way, 1 over 2 pi sigma square e minus half x minus mu over sigma whole square. Yeah, and the popular bell-shaped curve. Where is mu? Here. As you go to the left or right of mu, it's a square thing here, so the left and right doesn't matter, that means it's symmetric definitely, right? And the e minus half, this exponential decay ensures that whether you go to the right of mu or to the left of mu, you are going to decay, है ना? क्योंकि माइनस तो यहाँ है, इसे तो माइनस देना नहीं, right? So it's always a decay. As from the mean, if you deviate from the mean, the chances are supposed to, the rate of decay may change, yeah, right? But otherwise the shape, the bell curve remains this, yeah. Okay, so that is the Gaussian distribution of a random variable. What about the Gaussian process? What is a Gaussian? When is xt? Now we want to say xt, this is not one random variable, it is some process xt, yeah. This process, which is now a collection of random variables, one random variable is xt1, another is xt2, xt3, so on, yeah, continuous in time. What makes this process a Gaussian process? So it's very interesting that if xt follows the Gaussian distribution, yeah, then it's not enough to say that the process is Gaussian. Okay. So let me just first define it and then we can discuss it. It's a very interesting this definition. You've heard of recursion in programming, maybe little bit. So a stochastic process xt with t in t, which makes it this t is a real numbers, so it's continuous process, is a Gaussian process if every linear combination of its values basically we're talking about xt1, xt2 and so on. If every linear combination follows Gaussian distribution. Okay, so it's a very interesting way of defining a process. So the process is defined in terms of the distribution. We are saying any stochastic process will be Gaussian if you take any linear combination of it. Okay, that linear combination should follow the Gaussian distribution. So what do you know? How can you write linear combinations? कैसे लिखते हैं?
It's kind of a central limit theorem, sir. Linear combination ले तो मतलब वो भी Gaussian बनते हैं, kind of central limit theorem.
Yeah. So a1 xt1 plus a2 xt2 plus a3 xt3 and let's say you go up to an xtn for any n and t's. Yeah, कोई भी ले लें इनमें से. Take any of those, make any linear combination. Those don't make it zeros because then it's just degenerate हो जाएगा. So if you make any linear combination of this, then
It also behaves as a Gaussian.
that linear combination, let's call that y t. Yeah, or in this case it will sum to just one value, so we could just call it y. Then this y has to have
Distributed Gaussian.
yes. Okay, if you can prove that for any general linear combination of that process so this necessarily says, what does it say about xtk, by the way, net at any point? You know, the process, random process, Gaussian process has many random variables. What can you say about the distribution of each variable? At this point, when we wrote it, we didn't talk about the variable, right? We said there is a whole process. If you make any linear combination of it, that linear combination has to have a Gaussian distribution. Okay. Does it say anything about this thing?
It will follow Gaussian distribution.
It will follow. Why?
Because linear combinate for every sum of any kind of a linear.
So to get xtk here, let's say I wanted to get xt3, what would I need to do? a1 0, a2 0, a3 is 1, an all zeros except at a3 is 1. That is a legitimate linear combination. So necessarily every variable in the Gaussian process will be Gaussian distributed itself. Okay, but there is a non-intuitive thing here, is that by this definition, and we also have that there could be a process whose every variable is Gaussian, but the process itself is not Gaussian. Okay, because it may fail this condition. It may have some linear combinations whose distribution is not Gaussian. Okay, so because if this every variable being Gaussian, if its general consequence were that then this would hold, we wouldn't need to go here. We would just say
ये तो for small sample size के लिए हमारे पास होगा ना, मतलब अगर small sample size ले हो सकता है तो साहब हम बाकी ना, अगर हम infinite process लें तो इसके बारे में कुछ नहीं कहा जा सकता. ये क्या है
इसमें infinite process the way we have written the general combination or anything, yeah, it is finite set n, yeah, but otherwise we haven't said how big or small it is, right? So you can take any number of values there, yeah. But what is important to keep in mind is that it is not enough to show that, let's say you sign a process and you show that every point in this process is Gaussian, and then you say, okay, now this process is Gaussian. That's not enough. Okay, not just every point has to be Gaussian, their linear combinations have to be Gaussian. So this guy has to be Gaussian, this guy has to be Gaussian, but then their linear combination A1 with this point, A2 with this point, A3, and for any A1, A2, A3 has to be Gaussian. Similarly, and so when you have to prove this, you have to prove it in a general way. Yeah, of course, we will not try different values and do that. You have to prove it more generally. So actually, in fact, we will not prove it here, but it can be shown that this is more like a summation, right? Linear combinations, yeah. But even the limiting cases of summations, okay. So limiting cases, Gaussian process, the integration and the differentiation of a Gaussian process is also Gaussian. Okay, so it also leads to Gaussian process provided that they exist. We haven't talked about when does the derivative or integral of a random process exist. वो जो आपने पहले पढ़ी है definition, they never considered randomness. They were looking at deterministic. वो जो x square का derivative निकालते हैं आप, वो assume नहीं कर होता कि x is random, right? So we will come to stochastic calculus in a while, maybe after 1 or 2 lectures, बहुत brief सा, to give you a hint of what happens. Right, so so essentially we are saying that the process here so if that means if we are saying that xt t in t, if we say that this is a Gaussian process, then basically let's say y1t made up of xt plus h plus xt, where t and t plus h are within t. This will, what will be the distribution of y1t? Also Gaussian, because it's a linear combination of two of them. Yeah. Similarly, y2, let's say we define it as xt1 plus, let's say up to xtn divided by n. This will also be Gaussian distributed. Okay. Similarly, you can think of any other values. Even limits, if they exist, so limit h goes to 0, xt plus h minus xt divided by h. This limit will also be Gaussian distributed. Basically, if it exists. Okay. If it exists, actually, then this is we say that this process is differentiable. We will come to that.
Process में भी random variable में भी सर अगर हमारे पास कोई एक simple point लेना, उसमें भी अगर change आ रहा है तो वो भी हमारे पास Gaussian नहीं आता है सर उसका change. जैसे process के लिए बात कर रहे हैं.
Chain process किसी एक xt को लेना हमने ऐसे. So that is one. Let's say you fix it somewhere. Yeah. So that is one random variable in the process. That has to be Gaussian distributed. If the process is Gaussian, वो भी होगा बिल्कुल. Right. So because that is a legitimate linear combination of it. So I will give an alternative definition of the Gaussian process and then we'll end it here. Next time we will look at development of the Wiener process and how it falls within 3 classes: the Gaussian, self-similar and Levy processes. Okay, 3 kinds of processes. It falls in the overlap of those. We'll see that, but I will just give a quick definition, an alternative definition of the stochastic process. Of the Gaussian process. Okay. I'm just thinking maybe we can have it for next time then. Because there isn't. Okay, we'll do it next time. Yeah. So we have done one definition of the Gaussian process. Now we will look at an alternative definition which involves matrices. Yeah. So, yeah. Okay. Let's close this.